Hi everyone, in this video we'll be looking into the histories of the atomic models that are fundamental to shaping the atomic model of today. Now, firstly, we're going to start with who came up with the idea of atoms and when. That leads us to starting with Democritus, who, from 460 BC, first came up with the concept and the idea of atoms. Now, he came up with the idea of atoms using pounded materials in a mortar and pestle. Now, when you pound materials in a mortar and pestle, you'll see that these materials become finer and smaller. Now, from this idea of large materials or substances becoming into smaller bits and pieces as we grind them, Democritus came up with this idea that all matter, all substances in the world, is essentially composed of small microscopic indestructible particles or these atoms. And so he came up with this definition or this rough idea of atoms as extremely small, indestructible particles. Now, based on this idea, we move next into John Dalton's ball model. And this ball model kind of came up from this really keen observation that elements hydrogen and oxygen kind of always combined in the same ratio and fixed proportion. So it came from the observation that the elements hydrogen and oxygen combined in fixed ratios and fixed proportions. And from this observation, John Dalton kind of derived a set of rules or a set of basic principles. First is that all atoms, all matter, is essentially composed of tiny invisible particles called atoms. And it's that atoms cannot be created or destroyed, much like a concept of energy. It's also that atoms of the same element are alike in every way. The next principle is that atoms of different elements are different. The last principle is that atoms can generally combine together in small numbers in order to form molecules and in whole number ratios. So we can't have fractions, so we can't have decimals. In whole number ratios, atoms can combine. Next, we move on to the plum pudding model, which was a model that was developed by J.J. Thomson. And this plum pudding model is quite significant in that it discovered the existence of electrons, and it did so by using a cathode ray experiment. Now, you may wonder what a cathode ray is. To sum up, a cathode ray is basically a beam of electrons that's emitted from a cathode in a high vacuum tube. So it's basically a beam of electrons. And now, what's essentially going to happen is this beam of electrons is going to travel through a high vacuum tube from one metal plate to another metal plate. And these metal plates are connected essentially by electricity, hence why this sort of electron beam or the cathode ray can travel. And we named the metal plate that releases the stream of electrons as the cathode plate, and the metal plate that receives these electrons as the anode plate. And now what J.J. Thomson did was essentially in the sort of vacuum tube wherein the cathode ray travels, charged plates were essentially placed at either side of the tube, and this caused the ray to be deflected away from the negative plate and towards the positive plate. So how this is going to look like is, say that we have the negative plate right here and we have the positive plate right here. The beam of electrons, also known as cathode ray, is going to deflect away from the negative plate and towards the positive plate. Now, what was really funny was this happened with all sorts of metals that we placed for the metal plate that was the cathode sort of plate. So regardless of which metal that we used for the cathode, the same result kind of was created, wherein we had the cathode ray bend or deflect towards the positive plate away from the negative plate. Now from this, J.J. Thomson kind of concluded that, this is a part of the subatomic particles that make up the atom, this sort of phenomenon that was observed with the cathode rays having to bend towards the positive plate, it relates to the subatomic makeup of all atoms. And then Thomson states that these are due to electrons, which had a negative charge. And this was kind of like the first time when the concept of electrons really came into the term electron. And based on this observation, J.J. Thomson announces this new plum pudding model. And it's called the plum pudding model because the pudding itself, it's kind of also like a chocolate chip cookie. The pudding itself is going to be known as the atoms. The dough part is going to be known as the positive charge. And the plum, or the chocolate chips, are going to be known as the negative charge, the electrons. So essentially what J.J. Thomson kind of fathomed of the atom was that we generally have positive charges as the dough, and sporadically and randomly we're going to have these little plums, or these little negative charges, which were essentially electrons. And what J.J. Thomson thought of at this time was that these electrons, or these negative charges, are held stationary. But we now know that these negative charges, or negative electrons, essentially show up and disappear in spaces called orbitals. And we define orbitals as areas or regions that have high probabilities of electrons showing up there. So we now know that this idea of electrons being held stationary in certain places is wrong, but that was what was thought of until that time. So in this video, we covered Democritus having to come up with the idea of atoms, John Dalton's Ball model, which essentially gave like the sort of first principles of what an atom is and their properties. We looked at the plum pudding model by J.J. Thomson, which essentially used the cathode ray experiment to come up with the existence of electrons and thus sum all of the anatomy of atoms into this plum pudding model, wherein it assumed that the pudding is going to be an atom and the dough is going to be the positive charge, and sporadically we're going to have little plums or negative electrons kind of embedded into the dough. So we've looked at 3 different types of models. In our next video, we'll be looking into the nuclear model, which was found out from Rutherford's gold foil experiment and which is more relevant to perhaps the nuclear models that we know of today.